please give us a short introduction to the topic, and then I will explain what codes are and how codes can be of help with your area of research.
Code biology is really relevant to the research that I work on, which is mainly in the field of analytical psychology. And that would be working with patients and their dreams and all that kind of stuff. And one of the classic elements of analytical psychology is the idea of archetypes, which is I think the easiest way to explain it would be to compare it to something everyone's familiar with. If you, say, grew up in Hawaii and all you ever experienced is 85 degrees and all of your family members are the same for generations, then suddenly you decide to go to Finland in the winter. Well, what happens when you walk out of the plane and it's 5 degrees outside? Well, you get a sudden cascade of changes that are oriented towards conserving heat. So things like your blood shifts to the internal organs, you get goose flesh, you get the Lewis reaction, and you start shivering and all that sort of thing. Well, the important thing to think about here is that you're experiencing a reaction to an environment that you have never experienced before, and even people in your recent family have never experienced before. Well, what the heck is that? So this response, of course, is encoded in the genome. It's a defensive, adaptive response to a situation that you might encounter. And it's been so important to the survival of all of the ancestors that it's just kind of there waiting as a potential. Well, that's basically the same way that I think we should start looking at archetypes. If you look at the literature of archetypes, you will get lost in a huge tangle of all sorts of discussion. And I don't think we need to go down the rabbit hole there, but suffice it to say that starting with a certain number of researchers within Jungian psychology, like Anthony Stevens and John Ryan Hall, there's been a really big push to say, all right, let's see if we can't orient this towards what we know about biology since Jung died in 1961. Can we connect this to evolution? Can we connect this to biology more? And so he started that work, and I've continued it since he passed away a couple of years ago, and a number of other researchers are involved in this as well. And we've been talking about how the paradigm of code biology might be the next step in this, and I think it probably is. And you can boil down my thoughts on how it relates to a paper that I published in 2024 called The Innate Story Code. And if you want, we can kind of get into that. But what really caught my attention about this approach to biology is the importance put on meaning generation as being intrinsic to the organism. And I think that was the key step that was needed in analytical psychology just as much as it might have been in biosemiotics, to where we'll quit thinking of meaning as something kind of arbitrary and in the head and some kind of airy philosophical realm, and something that's actually intrinsic and embedded within the genome and all the different codes that are produced there. And just like a species important situation like very cold environments can trigger a physiological response, like the cold response, that you've never encountered before but has been lying dormant there waiting, I think that you can look at what we observe clinically as archetypal responses in the same way. We can say that certain species-specific psychosocial situations can trigger an archetypal response in the same way, something that's been there waiting for the right moment to trigger to help us adapt to that situation. Examples would be things like coming of age, triggering a hero's journey type of spontaneous thought, dream, or image, or say the importance of mentoring, triggering dreams about the wise old figure in the forest, providing wisdom, that kind of thing. It influences our folk tales and myths, influences our dreams. And as a clinician, I look at that and I think, well, I can sit here and try to boil this down to something that might have happened to you specifically in your developmental history, or I can look at this as something species specific, has more to do with our ancestral history and an ancestral need that is required. So there's my approach and my use of code biology and analytical psychology in a nutshell. So, we can go from there.
Yeah. So the question this is a complex topic, but what I want to address today is what codes might do or can do in this regard in explaining the problem of inheritance of these archetypes. So if we think of animals, it is long known in biology, you have so-called inborn behaviors. And the question is, from a human side, what can be inherited in terms of certain behaviors, responses, or even, let's say, mental concepts when we come to the archetypes? So is there something like a concept of the mother, the father, or is there, when you see animals, there is the puppy scheme, it's called. So they normally won't kill or won't harm the babies, because they have a kind of reflex that says, no, this is a puppy, I don't kill it. So this is inborn behavior. And the question is, how many of these kinds of inborn responses we as humans have, and how can they be inherited? This is the big question. Joao has answered the question that the same code principle applies to the archetypes as we see in code biology. But now I want to address what about inheritance and to give a reminder of the different types of codes. Okay, so I will just start with the very fundamental of what constitutes a code. This is according to Marcello, and it is based on a genetic code. So we have a world 1 and we have a world 2. We have an adapter, and these are macromolecules in organic codes. And on the other hand, the logic behind this is we have a code maker, we have the arbitrariness in terms of certain rules, and we have a code user. This is the logic. And what is the output of a code? It's a molecular artifact. And the example is the genetic code. Here you can see you have the codons on the messenger RNA. You have the loaded tRNAs where the amino acid is attached. And you have the single amino acids. And the code maker in a genetic code are the aminoacyl tRNA synthetases. And the rules are those of the standard mappings of the genetic code. These are the rules. And the ribosome uses the components of the genetic code and the rules. So it is the code user. We are not here in biosemiotics. Biosemiotics would say the ribosome, as Jesper Hoffmeier, is an interpreter, but no, it's not doing interpretation. It is just using the components, and that's it.
Right.
So there's a code maker and the code user. And when you look at this, you have 6 points you can name. World 1, adapter, world 2, code maker, code user, and the rule. And this I will publish in a paper. Give me, for any claimed code, give me these 6 criteria. Are they fulfilled or not? It's very easy. I want to remind everybody of this. And in this example of the genetic code, the artifact produced is a protein. In the genetic code, I call it a translator. It's a translation from one world into another world. And it's also called in biology, it's a translation machinery. Yeah, the ribosome is the translation machinery. But there are other codes that, for the time being, I call them transcribers. They are also organic codes. So what are they doing? There is some form of molecular ink, and there is an enzyme, and there is a medium where this ink is written on. And mostly this is a protein. Sometimes it is DNA or RNA. In the logic, you can find in the code list many codes that have this logic where they say there is a writer and there is a reader. Sometimes there is an eraser that can delete the written text. And what is the rule behind it? The rule and the logic behind this type of code is that there is a certain pattern. In some papers, they speak of this Braille language. These Braille patterns, these are for blind people, three-dimensional dots, so they can read by touching. In many papers compare the histone code or the epigenetic code on DNA, they compare it with this Braille language. So again, as we are talking of an organic code, the outcome is a molecular artifact. So here is the example of the histone code for the above shown logic. The ink can be the acetyl groups, and the enzyme attaching or writing with this ink is the histone acetyl transferase, and the medium on which is written, or the paper, are the histones. So the writer on the right side is the histone acetyl transferase, and the reader are so-called bromodomain effectors. So there can be a wide range of proteins that have a so-called bromodomain, and this bromodomain binds to these patterns of acetyl groups written on the histones. And this is happening on the N-terminus of the histone tails. So what we can say, we still are here at an organic code, and it has the same logic as the genetic code. You can list 6 entities that are relevant or needed for this code. And the artifact is again a molecular artifact, or what I call here this Braille pattern. But now we come to the neural codes, where the situation we will see changes a bit, and they are in a way transformers. And the basic principle is here that you have 3 different classes of neurons, and one class of the neurons is an adapter. And the logic behind it is you have an encoder that produces an excitation pattern, and you have a decoder that can read this pattern. So, and the thing here now is, this is no longer a molecular artifact, but it's a mental artifact, what this code produces. And I use here the example Marcello has presented years ago with his definition of the neural code. And this is the example of the sensory motor circuit. So you have a sensory neuron. Normally, you have to say you have always populations of all of these neurons involved. It's not that you have one neuron, and another, but there are many of each instance. So you have sensory neurons that are from the sensory organ. Then in the brain, you have an interneuron that is responsible for making the connections and the processing. So you sense something, it is processed, and then you react. You need to sense, and then you need to control your muscles to react to what you see or experience. So this is what this specific neural code encodes. And the point here is where it becomes different from the regular organic code is 2 points. We are dealing now with these electric patterns of neurons. Neurons fire certain patterns and they can do it repetitively. And this is not bound, let's say, to certain molecules. This is the first difference. And the second difference is that the code maker we have seen before always was a protein, an enzyme who was doing this. But in the nervous system, when it comes to the firing, there are many intrinsic properties of a neuron that constitute an embodied configuration. So it depends on the number of involved ion channels. It depends on the repolarization speed of the neurons. So there are many inbuilt factors in the neurons that determine the firing pattern of these specific neurons. And so the firing pattern is what is the rules are based on the firing patterns, but the firing patterns are not determined by a single entity. The firing pattern depends on many different constituents. So this is a major difference between the other organic codes, that you have this kind of embodied configuration in the neurons. So this is, and here you have some, maybe you call it image or a call to action. So what is produced in this circuit? In this circuit, it is produced that you experience, you touch something, you see something with the sensory system, and then in the motor cortex, it's in the cortex, there are many areas which are responsible for different sensory input. It is in a way processed. So this is the difference we have here with the neural codes. So this is in principle how these two work. And where can you, let's say, modulate or change this code? And this is here in this embodied configuration. There you can change it. Yeah. Okay. And now I want to make a further difference. When we come back to the problem of the inheritance of archetypes, we have here the problem that we as an individual, we have the nervous system. We process entities in the nervous system. So what you see here is the LTM is the long-term memory, STM is short-term memory. And there is something like synaptic weights. These are, let's say, configurations of the neurons that determine how things are saved in the nervous system, how we learn and how we memorize. So basically our memory has an encoder and a decoder, and it is also based on these excitation patterns. So we can make memories in this way. But what happens? How should this be inherited? So when it comes to the egg and the sperm, there is only the DNA and the histones. There is no nervous system, there is no memory, there is no storage, there is nothing in the brain. So you could say that when you come from a Freudian perspective and would say in the extreme, everything depends on your personal development. You could say, okay, this one, what you see now is sufficient. Everything is saved somewhere in the brain. It could be in the nervous system saved. It doesn't need any archetype at all. That has to be transmitted through generations, because it can be saved somewhere in the long-term memory. But as the sperm and the egg, they have no nervous system, nothing can be saved, everything is deleted. So where can memory be made? So individually, of course, we have our nervous system, but I call it when it comes to the group level or to us as human beings, where over these thousands generations can archetypes then be at all? And Then the only thing that remains is the genome and let's say the epigenome, because when the sperm and the egg unite, the classic epigenetic marking on the DNA is deleted. The only thing that is inherited is the genome and histones. Histones can be inherited with markings. Yeah, there are many. I showed only the acetyl of the histones, but there are at least 13 other inks that can be written on the histones. You can see it like different colors on the histone. There are at least 13. So these can be inherited. So there are only two ways where I would say, from a biological perspective, how can inheritance of archetypes be accomplished? So you have to look into the genome and the epigenome only in the sense of the histones. This is how any type or any kind of archetype can be transferred from the past to the present. And we have to make a difference between inheritance on the human race level and on memory on the human individual level. So this is what I want to put here, that there is enough room in principle to store archetypes in the genome or in the epigenome. How many combinations with all the histones and at least 13 different molecular markings or molecular inks, how many combinations of storage you can have? Yeah, it's amazing. So in principle, and this is what I was in conversation with Eric. I say in principle, and there's a big discussion in his field. In principle, it is possible to have all these things stored, nearly endless potential of storage. But me personally, I would doubt that everything is stored, every archetype is stored. So because the principle of codes is you can create novelties and new things with very few rules, and you have a lot of different sets. And I will start this again. This is just a short or very quickly drawn illustration. When this star is symbolizing a group of humans or a population that reproduces over years and hundreds of years, and if you tell me there are certain archetypes, the question I ask is, how many archetypes do you think there are? Because when you think how quickly our environment changes, our culture changes, literally the artifacts we have, the items we produce, everything changes very quickly. So from an evolutionary point, would it make sense to save all these somewhere in the genome? It would not make so much sense in my view. But there should only be, let's say, basic archetypes being saved, and these archetypes, and this is the beauty of codes. I will show in the next slide. We have seen that we have always different sets. We have a world 1, which is a set of components in a genetic code. We have a world 2, which is a set, and we have a set of adapters. We have a mapping. So we have in our genome certain, let's say, archetypes or behavioral responses that were needed over and over and over again. Not an endless number for every situation, a new archetype saved, but for the core themes. And these core themes can be reassembled and mapped to new occurrences in the environment, to new situations. This is what I would give to Eric to think and to discuss later on today. If this would match your expectations of what code biology provides. Because I want to give another example I did a training course in the software GIMP, which is an illustration program, and they showed with how much creativity and how much things you can draw with 3 basic forms, with a circle, a square, and a triangle. You can make so much out of these 3 by just recombining it and combining them. So the question is then, when we think of human behavior, we have an individual history. We have, since we were born, we have a nervous system. We can save certain things in the long term and in the short term memory, of course. But for our reactions, there are other intrinsic, let's say, things that are of importance that are, it's called affective, what is it, Eric? Affective
Affective
science?
neuroscience, yes.
Yeah, affective neurosciences describes them. So you have the emotions that shape our responses. So you have intrinsic motivations, and there are clearly identifiable kinds of emotions that all shape your internal state, and they will, in a way, contribute to the encoding of your behavior towards a situation. And with them, these intrinsic components, and they are all in a way coded in themselves, they contribute to your behavior. And from this limited set of what is really saved in the genome and epigenome, they will do, or there will be a mapping to the situation, to the world we experience. So I think my generation lives in a very good world. We have everything in a way we need. So there is no starving, nothing like this. So maybe this changes, but it has, at least for my generation, this has changed compared to my grandparents. So the human brain, and we have to react to situations that are always new. So there cannot be a principle, in my view, that saves everything as an archetype, every situation as a kind of set. So there would be really big sets of responses saved to, or situations saved. So this is the idea behind it. There is a limited set of emotions that is described in the literature we have. You see this here as a colorful wheel. And this is a set that is combined then with certain, let's say, core archetypes. And in certain situations, they will combine. And this is here like this one-arm bandit. It is not like this is by chance. First, in evolution, it appears only that this is a chance combination, but over evolution, you can predict the combinations of these apparently independent reals in this one-arm bandit that make up your behavior. And I think Joao and Eric, you're very good in predicting people's responses. So you know that this is not a random machine, but it's highly predictable. Yeah. So this is what codes allow, this mapping, and what code biology can contribute is to the big question, what can be saved from generations. So Eric and Joao, you maybe also concerned with people having traumata, and there's a literature in many is known about the epigenetic codes of people here in the World War II from the Netherlands and some other countries. There are archives, people starving, and this starving, especially the acetyl groups, they are related to the metabolism. And when you have not the proper nutrients, metabolism affects your epigenome on the histone level. So there is a way how this can be translated and inherited. And then the question is, okay, if people have traumata, what does the epigenetic changes induce on the genome? And then we come back, we could say, okay, when there is a nervous system, and it depends on the configurations of the neurons and their firing patterns. I'll try to find it. Where is it? It's the embodied configuration. So what you can say, there are few studies, very few. But when you have these epigenetic changes, what can they affect? They can affect that when during the development the nervous system forms, that there are certain preset configurations of your nervous system. So there can be, let's say, maybe you starving because you have no food. And this affects in your egg the histones. And then in the developing embryo, this affects how the nervous system develops. And maybe it is the case that the nervous system is in such a configuration that the child is anxious. It's always afraid. And this could be an effect of a trauma, that it is afraid. So what you can change is, let's say, some basic configurations. So configuration is a very important term here, especially with the nervous system. So what you can then inherit is some fundamental structural properties of your nervous system. This is a way where code biology can help to answer questions that are pertinent to Eric's and Joa's field of archetypes. And I hope Eric, you can now jump in and tell us more about if this goes into the direction answering your questions.
Yeah, it does. I really like the way that you put this together. One of the debates that's been going on in analytical psychology since the early 2000s, really, was since Anthony Stevens and a few others had proposed that archetypes are inherited on some level, to some degree, a significant degree. There was a counter argument that at the time people were saying in the 2000s, they were saying that, well, there's only, at that time they thought there was about 30,000 genes on the genome. Now we know there's even less than that. And they were saying, well, that's not enough genetic information to encode anything significant that would encourage the development of particular imagery. So when I came on the scene around 2010 and started writing about this stuff and debating with these individuals, I complained about this back then, saying, well, no, that's ridiculous. Number one, there's no agreed upon number that is needed for one thing. Like how many genes does it really take? They can be combined in nearly infinite ways. So, but more importantly, what this does here, as you're pointing out, that you have more than just the genetic code. You have the histone codes, and I didn't hear you mention the methylation code, and I'm assuming that's also part of the histone complex, but that's another mode of information transfer across generations. Am I right about that?
Yeah, the DNA methylation code is the one code that is not inherited. This code is deleted during spermatogenesis and when the egg develops. So this is not a way of inheritance.
Okay.
I mean, there's an epigenetic methylation code, but not in humans, not in eukarya. In bacteria, it's a different story. Yeah, okay. That's inherent, but not in humans.
Okay, so not relevant here, but you mentioned the 13 different histone codes that are. So, given the fact that you do have, that opens up the possibility that, oh yes, there actually could be quite a large amount of information inherited to produce this. But the point that you made earlier, not every situation needs its own archetype, is absolutely correct. And it's been a key element of archetype theory from Jung all the way back in the 1915s and on, that affect is extremely important to it. So that was taken up later by later theorists, and the movement was made to say, okay, then this needs to be, an archetype needs to be connected to evolutionary adaptation on some level. So while, yes, the human organism has a large range of learnability and a flexibility in terms of behavioral output, there's going to be certain situations that trigger an emotional response, kind of like an instinct, although that word itself has a pretty complicated history, but that it would likely produce particular images. Now, the way I look at this is that generally in the process of spontaneous thought, so in one of your slides, you mentioned the interneurons, like, so you have the sensory neurons, the interneurons, and the motor neurons. Well, the interneurons, that's a small word to cover a massive amount of stuff that's happening, because you have the brain itself has an intrinsic activity to it. It's not just sitting there waiting for sensory data. And we know this because when you're asleep, the whole sensory apparatus is shut off, as well as the motor apparatus, and it's just all intrinsic activity and processing. So what happens there is, through the machinations of the default mode network, largely, you have the production of spontaneous images. Well, if you start looking at the content here, that's much of it is metaphorical in nature. So you can take these metaphors and break them down into primary irreducible metaphors. And the way I look at this is that some of those are going to be innate in the sense that they are path independent. So whether or not they're actually encoded specifically in the genome, that's a difficult question to answer. But simple things like representing anger as heat, why would that emerge as a metaphor that the brain uses? Well, it's simple. It's the fact that every nervous system is set up to where, when we trigger that affective neural system of rage that you mentioned in affective neuroscience, body temperature increases, and that's the configuration. So that's the piece of the puzzle there that you pointed out. The embodied configuration makes a massive contribution here. So then the brain then looks at that and goes, well, if I'm trying to organize my thoughts, then I can easily make that connection between anger and heat. And in fact, that metaphor, which in English anyway is responsible for more complex metaphors like boiling over with anger or burning with rage and that kind of stuff, those are kind of metaphors that we're going to use regardless of what culture you're in or regardless of how your individual history is set up, because of the body. And the configuration of the body produces that metaphor. And so the way I look at that from a point of view of code biology is that the human body itself is the adapter. The arbitrariness is that there is no semantic connection between rage and heat intrinsic to either concept. You have to have a body in order for that encoding to occur. So the code product of that metaphor then is the embodied configuration. So then that metaphor can be used to create all sorts of spontaneous thoughts. And those that are involved in, that are triggered by important situations to Homo sapiens, most of which are psychosocial. Yes, we do have to worry about predators and all that sort of thing, but a huge amount of our survival has been bound up in social interaction because we're such a socially cooperative species. Well, then that means that I think over evolutionary timescales, certain situations like possibly being kicked out of the social group, or loss, or seeking a parental figure, or seeking a mate, all of that stuff is going to have been so important to survival that it will be likely, in my opinion, to trigger images that use these innate mappings, those mappings that just use the body to produce the meaning. So that's how I look at things like dreams and visions and all that are spontaneous products. So honestly, I think that the code biology perspective organizes a whole lot of this thought and makes it a lot more precise. Because before we would look at things and just kind of have this dialogue about it without a whole lot of biological anchor. And before the code biology perspective, we had to make kind of vague references to the genome and say, well, it's got to be in there somewhere because it's adaptive on some level. But with this, it gives us the mechanisms specifically. And a lot of this depends on how you define the term archetype, which is its own big problem in analytical psychology. Jung was grappling with his strong intuition, and his writing is sometimes a little bit hard to follow. And so there's been lots of conversation about that over the years. But I think at the level at which most people can agree, it is something that is a spontaneous, emergent, or a spontaneous metaphorical narrative that is in response to an important species-specific situation. And most of them that we deal with anyway are psychosocial. I think a great analogy to this would be the conserved transcriptional response to adversity. And I'm not sure if you're familiar with that particular psychoneuroimmunological thing, but when people have disruptions in major attachments or rejection or trauma, it triggers these cascade of changes in the immune system that leads to a very inflammatory, pro-inflammatory state. And that's an example of a psychosocial situation triggering a physiological response. Now, when I spoke with Stephen Cole, who's one of the lead researchers in this particular phenomenon, he asked me, after looking at what my research was about, if there had been any studies on whether or not that state triggers specific imagery. And I said, well, not that I know of, but are you interested in doing a study like that? Right. And yeah, so I think it's theoretically possible to show that kind of biological connection. And because the conserved transcriptional response to adversity exists across mammalian species that are social, it's obviously in the genome and the epigenome to some degree. And that's really all I'm talking about. I'm talking about situations that trigger specific types of narratives in dreams and spontaneous thought. Well, then that's an archetype right there. And we don't need all of the other confusing sidebars. And I think code biology really provides that, especially with the things you pointed out.
Yeah. And
I don't know if that answers your question, but it was a really long sidebar.
I just want to add now, if the screen can be shared again in full. See it. To do it. Let's see. No. Now it's coming. Okay. So I just want to show here what I mean. What can be saved in the histones, in the epigenome. And the point is, this is not some physical way these archetypes could be saved, like a heat produces something, or a heat pattern, or a cold shock induces something. The point is, it is really encoded by molecular machines from the metabolism, or as Eric said, there is a big emerging field of this neuroimmunology, where certain stress reactions cause measurable immune responses. And these immune responses, they can very well precipitate into histone modifications. And for those who are not familiar with the histones, I want to share these few slides here. The DNA in eukaryotes, or for this case here in humans is shown, is wrapped around proteins. And histones, there are different types of histones, 1, 2, 3, 4. In total, it's 8 per such complex. And the DNA is around them. And you see here is symbolized on this side, epigenetic mark, it's called. This is a symbolized N-terminal tail of one histone, where these modifications can be done. And you will see that the variability of the histone code is, or the combinatorics is magnitudes higher than for the genetic code, the combinations. So I will not go to this, the functions. Let me see what this is. No, then I will go to the combinations. So this is a table that shows different histone variants that are available. All these here in blue you see are different histones. And so you can count them, and then you can see how many combinations are possible only with different histones. And when you try to create every combination, let me see.
There's an astronomical number of possibilities there.
So this is indeed an astronomical number of potential combinations you have only with the existing histones. And then when you consider the length of the DNA, where you can have this, you can write a lot of text. And when you think you have 13 different molecules from histone, from acetylation, methylation, citrullination, there are so many modifications possible. It's an endless way to encode information in principle. So from immune responses to metabolic responses, everything can be stored in the histone modifications. So this always pronounce that the histone code is the most complex organic code we have. Yeah, there is nothing, and there you have even further codes, because one ink in the writing of the histones is phosphorylation, phosphoryl groups. And the phosphorylation code is described as a known code. So you cannot only have phosphorylation on the histones, but on many other proteins. They are dependent on phosphorylation. And there are many. So the histones are an hub for different codes interacting at the inheritance level here. So while it has to be proven, and the question is how it can be proven, that these archetypes and behavioral patterns are inherited, but in principle, the possibility is there to encode this in the epigenome. Yeah, This is what I want to show with these slides. It's not like having a few combinations and that's it. Yeah, it's much more complex. So you see here a representation of only the most common modifications of the histones, and these lines are the N-terminal chains of the histone 3, histone 4, and so forth. And you see you can have many different combinations of these core markings here, and they all have a meaning in a way. They encode information in the histones. So this
the letters. Oh, I had a question.
Yeah.
The letters K, S, and R, those are different histone molecules.
Those are amino acids in the histone tail. So not every modification can be done on the same amino acids. So for each amino acids, there are certain molecular inks in a way that can write on them or not.
Okay.
So the letters in these tails are amino acid.
Okay, but then each of those there you go, the 13 different inks.
Yeah.
So each histone can be modified by one of those or more, right?
Yes, but some of them can only be modified by one.
Okay.
Yeah.
But that's still an insane amount of potential encoding.
Therefore, I say it's really the most complex code that we have.
I had no idea it was that involved.
Yeah. But yeah, this is the perspective code biology can offer. from different angles. So,
Mhm.
and I hope that in the future we may have a more clear picture how the neural codes contribute to this. And you rightly pointed out that the code with the interneuron is only a very limited code. It's one example. As you said, many connections in the brain itself, they don't depend on interneurons. Yeah.
Right.
So this is the point. There are many more neural codes, but I just gave this example because it's a very clear and simple to illustrate. Yeah.
Yeah. But you've got in the brainstem and the midline subcortical structures that those neurons are attached to all kinds of physiological non-neural structures like the endocrine system, the immune system, and so forth, the heart. And there's constant feedback there.
Yeah.
Yeah. So that's the state of the body affects the mental state. I think a really important thing to point out here is the one stage in the neural codes that Dr. Barbieri points out is the neural and the organ response mapping onto mental artifacts. That, as he pointed out, is basically crossing the mind-body divide. And at that point, then you have mental artifacts piling on top of this using their own code system. So you can see we've got codes on top of codes on top of codes, and that's one of the problems, of course, because I'm trying to go from the genome to an image, and there's many steps there. But this provides really the kind of grounding that says not only is this possible, it's likely, especially if, and correct me if I'm wrong here, but the information that's stored on the histone codes is likely to be similar across humans.
Yes, I would say so. Yeah.
Yeah,
Definitely.
right. So there's a massive amount of like basic, this is the plan for a Homo sapiens that is going to be very similar there. And
Absolutely.
so these the potential, like the example I gave of the cold response, where or the diving response is another one, right? You may never need this in your whole life. You won't even know it's there unless you specifically encounter this one situation. Like there's more than enough room in this storage, transfer to have many potentials like this.
As I said it, yeah, you were right. So most of us, as my boss would say, you never come out of your comfort zone. So you will never know what kind of reactions you are able to produce.
Yeah.
But this is a very good example you have. There are these cold shock responses, yeah, and there are many other responses that are or were at least useful in the past and that can be retrieved, but it needs certain triggers or circumstances to produce them.
Yeah. And it has really nothing to do with your prior personal history. It has to do with the species history.
Yeah.
Now, and here's an important piece of this is that the cold response, since I'm using that as an example, I think it maps nicely as a metaphor for how the archetypes work, because it can be modified. Like you can become more accustomed to cold weather. Like the cold response can be fine-tuned through development. So it's a combination of a inherited potential that is then piled on with experience that can shift it. And that's exactly the same way that archetypes work. Is how the basic plan of the narrative that you experience in a dream is inherited, but your personal development can pile on stuff on top of that. So one good example that you see from research in dreams comes from Christian Russler and his group, where he looked at a series of dreams of people in psychotherapy, and there was a particular image that popped up consistently, and that was of a child, a special child. And the idea in psychology is that the child represents the new element of yourself that you're trying to work on and develop and usher in So it's a metaphor for your own particular development. So that popped up so consistently, and Jung talks about that as being a type of archetype that also appears in mythology and folktales. So what is happening there? Well, it could be that the basic plan is inherited, i.e., I'm engaged in this process of personal transformation. How do I map that? How do I understand that? I use these metaphors, and the child metaphor, since I think we all have infant recognition mechanisms embedded, would be a readily available configuration to image as a metaphor of that inner process. But that's just one example of many. Yeah. The other ones I gave too, like the anger is heat, that's found in languages all over the world. And I'm actually currently, if anyone's interested, you can contact me. I am doing a study right now on these innate mappings in multiple languages. To date, we have collected data on 35 different languages. I'm basically testing the idea of innate mappings empirically to see if they exist across multiple languages. We've got everything from Afrikaans to Zulu, and even things like Old Irish. So some dead languages are thrown in there. So we do have a few Italian and maybe one or two Portuguese, but we could use any language, and more data points is better. So that's my advertisement.
Yeah, great. So to sum up, what for me as a biologist and as a code biologist is the most interesting thing related to your work. So when somebody on an individual level experience any kind of extreme situation or whatever you will call, and they come to you for therapy, and ever this comes again, they report some stories, some archetypal pictures. We have seen then what has happened. There has been on the individual level established a new code. But what are the circumstances that a situation leads to the manifestation of this mapping that is then recalled under these, let's say, phylogenetically inherited level of archetypes? So maybe there's a stressful situation or a cold situation that is mapped to the wrong response in a way, and so this will pop up again and again. So what we see is that took place a new mapping that you can observe with a patient. There was a mapping done, and for me it's interesting, how was this done in this situation? How is it possible that some situation is now connected, mapped to certain archetypal behaviors? But from my perspective, this is what happens then in such situations. There is the establishment of a new mapping.
Mm-hmm. Yeah, and it's like the productions, the new mappings, like the psyche is doing this all the time. It's always trying to figure out the process of memory consolidation, identity formation, emotional regulation, and future planning. In this process, it's creating new mappings all the time, but the language that it uses to create those, I think there's a significant and inherited component to that. So things like the anger is heat and the danger is darkness and all that kind of stuff, that'll be there as part of your alphabet. And the brain can take that alphabet and construct new metaphors. And I think what happens is in these very commonly encountered serious situations like coming of age or trauma or dealing with, mating on all the drama there, it'll give you stories that have the same basic pattern, but there'll be unique combinations in there from the individual piece. So it's I think at one point, in code biology, he talks about the codepoesis capacity of the brain. Like it's got this ability to just constantly make new codes, neural codes all the time. And I think it's absolutely right.
A few brief words of gratitude for this truly extraordinary gathering we have shared over these 3 days. Thank you very much, Robert and Eric, for this magnificent dialogue. Analytical psychology and code biology have much to gain from their interpretation. And now some final words. We once again have a wonderful group here in Guimarães. This leads me to express my deepest thanks to Professor Ricardo Machado, President of the CCG, a remarkable house of innovation and technology that so generously welcomed and supported us, as well as to its collaborators, Isabel, Mara, Ana Costa, and Rafael. I would also like to extend a very, very special thank you to my own team, whose dedication and diligence were essential to making this event possible. Cristina, Sandra, Susana, Ricardo, and Carla. I will carry wonderful memories from this conference. And I must confess, since my days as a newcomer in Prague in 2009, to organizing the gathering in biosemiotics in Braga, Portugal in 2010, and then welcoming the code biology community in 2023 and again in 2026 here in Guimarães. Seeing from my point of view, I'm sure that code biology will endure. Personally and scientifically, I am fully committed to helping carry forward this extraordinary field of knowledge, founded by our dear Marcel Barbieri. Along the path he opened, we continue and we shall continue. Joint papers will emerge from this meeting. New friendships have begun, and older ones have deepened. Science and life together are preparing for a new era in this strange world in which we live. A world from which we neither can nor wish to escape. New solutions will be found, and indeed are already being found, and our work will become, I'm sure, part of the solution. Let us take this mission into our own hands. Thank you all for everything. I look forward to seeing you again next year in new and inventive ways. See you and thank you. Thank you, Eric. Thank you so much, Eric.
It was great to be here. Really appreciate the invite. I hope to make it there in person someday.
Of course.
Maybe next year.
Thank you, my friend. Thank you, all of you. Thank you.
So we are finished.
Oh.
For now.